So I thought this was just interesting. Before we go on to 15.3, there is an Are You Ready for More at the bottom of this Retire a Millionaire one. If Noah is 15 years old and wants to retire a millionaire when he's 60, if he invests $1,000 today, what would his interest rate need to be in order for him to achieve his goal? Kind of a nice backwards way to think about it. Then he could shop it around and maybe find a bank that would be willing to give him that interest rate. So there's some interesting ideas going on there. So I found out that that would give him, if he's 15 and he wants to go until he's 60, this investment, it would give him 45 years to get there. So I set up this equation. He's starting with $1,000, continuously compounding at an unknown rate. So there's our new variable, that R. And we know it's going to be lasting for 45 years to see how long it takes to equal $1 million. We could graph this, we could calculate it, we could do all kinds of great mathy math to it. I like mathy math myself, so I'm going to divide both sides by 1,000. Find that e to the 45r is going to equal, let's see, cancel, 1,000. Roll that e to the other side, a nice natural log of 1,000 happening here. And to isolate that unknown rate, just dividing both sides by 45, what we would need is a rate. Let's take that natural log of 1,000, divide it by the 45 years that we're giving it, and R equals 0.1535. So he would have to find a bank that would be willing to give him a 15.35% interest rate. Banks won't do that, but his investments might, so he's smart. He could definitely start with $1,000, find some really great investments, and he could make that happen. Let's move on. If you have never lived through a cicada infestation, you, my friends, have not lived. They are hideous, they are loud, they are annoying, they get in your hair, they get in your food, they are all over. They come out every 17 years, and they make a non-stop, consistent buzzing noise, day and night. It's enough to make you feel like you are living inside of a machine. And they're there for like a couple months. So we just recently had an infestation. If you're interested and curious, go look up cicadas. But a population of cicadas is modeled by a function f of w equals 250 e to the 0.5 w, where w is the number of weeks since the population was first measured. Explain why solving this equation gives the number of weeks it takes for the cicada population to double. Well, if it's doubling, we start with 250 cicadas. And doubling that would equal 500 cicadas. And I see that 500 right here in the equation. So, yep, this would be finding out double the population. How long does it take for it to double? And then it asks us, well, hey, how many weeks does it take for the cicada population to double? We're right back to solving equations, just like we did in, what was that, lesson 10? Just now we have a situation. So every time we are doing this, the first thing that we have to do is to isolate the base and the exponent. Right now it's multiplying by 250, so I'm going to take an opposite operation and divide by 250. We already said we want it to double. I have a base and an exponent. I need to isolate the unknown exponent, so I'm going to roll this e to the other side. Rolling an e makes it a natural log of 2. And our last step, in order to solve this, we would have to divide both sides by 0.5. We need to find the natural log of 2 and then divide it by 0.5 to find the number of weeks that this would take. I'm going to use my cell phone calculator today. Natural log of 2, natural log, there we go. And I need to take that value now and divide it by 0.5. 1.386 weeks. So it'll take us about a week and a third. Pretty cool. It then asks us to use some graphing technology to graph y equals our function and y equals 100,000 on the same axes, and why we can use the intersection of the two graphs to estimate the time when the cicada population will reach 100,000. Well, if we put them on the same set of axes and we want to see what's happening there, I see a y and a y equals, so maybe we're going to use a graphing calculator or a Desmos, either one. And if our function f of w, it already told us that that's the population of cicadas. Oops. Sorry, put the s first. So that's our population of cicadas using the f of w. And finding where it equals 100,000. So setting them equal to each other just means they're happening at the same place and the same time. So that is when the population would equal 100,000. Let's go use a Desmos and see, because it tells us use graphing technology. I'm going to clear out what's in here. And I have an equation that started with 250, multiplied it by e, raised it up to, here's our exponent, 0.5 unknown x. Man, that's a cool looking graph. Look at how high that gets out quickly. I'm going to change my settings so I can see a little bit more going on here. If I just went from a like a -2 to 10. Here's what this looks like in 10 weeks time. Oof, not even, in 4 weeks. It goes from 250, up to a very large number. I want to know when this is going to equal 100,000 cicadas. Well, I'm going to have to zoom pretty far out there. I don't like just zooming out, so instead I'm going to go change my y-axis maximum to be over 100,000. I'm going to say 110,000. And now I can see that line at 100,000. I can see my cicada population, and I see that this is going to take almost 12 weeks. So to show my work, remember, please, if you are showing your work, what we want to do is actually show it. We can show our work when we use the Desmos by showing what the graph looks like, where our two lines cross. This is the 100,000 line. And finding that ordered pair. Let me click back over because I already forgot what it was. 11.983. And so drawing a graph, sketching a graph is showing work. I can see that this would take me about 12 weeks for the population of cicadas to go from 250 to 100,000 noisy, annoying, loud cicadas.